Yes, you are live, Marcus.
I see that.
Welcome from Netzsch Instruments to our new Research Spotlight series. I'm your host, Peter Vikos. The Research Spotlight series are virtual presentations from Netzsch users on a wide range of applications, demonstrating how our thermal analysis contributes to their research. Today is our nuclear materials session. Over the past few weeks, our sessions were on first polymers and second metals and ceramics. These were recorded and are now available for viewing. If you have questions today, they can be sent to the questions bar located on the tool section of GoToMeeting. We will answer questions at the end of the presentation. Let's get right into our session entitled Thermal Analyses of Advanced Nuclear Materials. Our speaker today is Professor Marcus Pirro. He is currently a Canada Research Chair in Nuclear Fuels and Materials at Ontario Tech University, where he leads a multidisciplinary team in support of both academic and commercial projects. Previously, Professor Pirro was the head of the Fuel Modeling and Fission Product Transport section at the Canadian Nuclear Laboratories and a postdoc at the Oak Ridge National Laboratory. Professor Pirro's primary research interests are in computational thermodynamics, nuclear fuel engineering, multi-scale physics modeling, and simulation of nuclear fuels and materials. He has also consulted in both nuclear and aerospace sectors for industry and government, both in Canada and the United States. I want to welcome Professor Pirro, and I'll turn this over to you right now, Professor Pirro.
All right, thank you very much, Peter, for the warm introduction. And thank you everyone for your attention today and for joining us for this online webinar. I realize that a number of folks will likely view the pre-recording at a later time. So I'll be giving a talk on thermal analyses of nuclear materials, and this work was done primarily with a few students and postdocs in our group, Ksenia Lopkina, Bernie Fitzpatrick, Ernesto Geiger, and a few other collaborators, which I'll be mentioning a little later. And before I get into it, I would like to thank Peter Vikos, Anthony Melita, and Melinda Tucker from Netzsch for the kind invitation to give this talk. It is very much appreciated. I'd also like to thank the efforts of some collaborators, Kan Sakamoto from Nippon Nuclear Fuel Development in Japan, Jim Davis from U of T, Chris Chobak from General Atomics. Thank you very much. Also, thank you to some other collaborators over the years as it relates to some of the topics I'll be talking about today, including Dr. Andre Benes from the Joint Research Center in Karlsruhe, Germany, Ted Bessman and Caitlin Johnson from the University of South Carolina, Daniel Clough for the Canadian Nuclear Laboratories for their fruitful discussions. And lastly, thank you very much to the Canada Research Chair Program from the Natural Sciences and Engineering Research Council of Canada, the Discovery Grant Program from NSERC, Ontario Power Generation, and the Canadian Foundation for Innovation. So what I'm going to talk about today is I'm going to give a bit of a quick introduction to our group. I'm assuming that most of you folks haven't heard of Ontario Tech, nor probably haven't heard of our group. And what I'd like to do is give 3 case studies of some research projects we've been involved with in nuclear materials as it relates to the use of a Netzsch 449 F1 Simultaneous Thermal Analyzer. And those 3 case studies are an accident tolerant nuclear fuel cladding, which is a product that's intended for commercial deployment, tokamak fusion materials, and lastly, molten salt reactor chemistry. Now, like, not to get too corny, but I think it is kind of useful once in a while to come back to the basics and return to what our mission statement is. At the university, the ultimate objective is really to train students and to help them prepare them to enter the workforce. And an excellent vehicle to accomplish that, at least for graduate students, is through basic and applied research projects. And our main mission in that regard is really to enable and objectively inform the nuclear industry to be successful in designing and operating nuclear generating stations in a safe, cost-effective, and environmentally responsible manner. So that is to say that we don't have a horse in this race, and the intent is really to be very objective in our approach and without bias. The other thing that I think is worthwhile to return once in a while is in regards to the concept of technology readiness as it applies to many different technologies. This figure here is commonly used by NASA to investigate different levels of technology readiness, where at the very bottom here, TR1, you basically have basic level technology. And as that basic level technology goes up in terms of greater knowledge and understanding in its performance, you go through multiple levels where you prove its feasibility. There's technology development, the demonstration of that technology, and leading towards commercialization and utilization by industry. And a lot of the technology readiness levels at the very bottom generally involve things that are too high risk for industry. And it doesn't make a lot of sense for industry to really be involved with a lot of these very high risk type of activities. However, that makes a great opportunity for research and development in academia. Similarly, at some of the higher levels of technology readiness, there's an excellent space for the national laboratories. In the United States, for example, the US Department of Energy has, I believe, 17 different national labs that are very well equipped to look at some of these intermediate level of technology readiness, including very large scale user facilities. And finally, industry has a role where once these technologies have reached a certain stage of maturity, this is where industry can take that and apply its own rigor in terms of making it commercially available. Now, the important thing to understand, at least in my interpretation of how this all comes together, is that knowledge and technology transfer is really the vehicle that traverses all of these different levels of technology readiness. Now, this is where we play a role in academia, similar to national labs, in order to make any particular technology commercially viable. Now, as far as our university goes, we were named Ontario Tech University. We were initially called the University of Ontario Institute of Technology, UOIT. No one could ever get the name right. I'd always get Ontario Technology, Ontario Institute, the University of Ontario, or sometimes even the University of Toronto. They're all wrong. It's a real mouthful. So last year, the university changed the name to Ontario Tech. Nice and simple, easy for everyone to remember. We're located about 50 kilometers east of Toronto, roughly considered part of the Eastern Greater Toronto area. We have actually one of the largest nuclear engineering programs in North America, which not a lot of people know about. We have a huge program that spans many different degrees and diplomas. We have a new center of small modular reactors that was established not too long ago, and this is really starting to beef up. And we welcome a number of visitors, but obviously after the pandemic. Here we have a photo of on the back side of my office area. This is by the library, so it'd be nice for you guys to visit after the pandemic. As far as our group is called the Nuclear Fuels and Materials Group. Currently, we have 16 members. Funny enough, in 3 different continents: North America, Europe, and South America. And overall, we have a balanced experimental and computational research program. This is very much intentional so that computational and experimental research projects can work hand in hand in a very cohesive fashion. We have an experimental nuclear fuels lab that is licensed to work with uranium, thorium, and tritium. And a key component of all of our research projects is partnerships. Virtually every project we have has a partner, collaborator, and I firmly believe that this is a key to success, where we can work together with other partners that have mutually inclusive objectives. There are 4 research themes that are conducted within our group. 1, nuclear fuel performance and safety. 2, spent fuel storage and disposal or disposition. 3, emerging nuclear technology, and 4, advanced manufacturing. So what I'm going to do is give a bit of a show and tell in terms of some of the research projects that we're doing here, all related to advanced nuclear fuels. And the first one here is thermal oxidation of accident tolerant fuel cladding. This project was in partnership with Nippon Nuclear Fuel Development in Japan, and was documented in this paper that is given here. A lot of the experimental work was done by Ksenia Lapina and Ernesto Geiger, and some preliminary work done by Daniel Hallett, a former student in our group. So accident tolerant fuel is a relatively new technology, but is intended for currently operating power reactors. And the impetus of this class of technology is broadly motivated by the unfortunate events of Fukushima. And so the basic idea behind ATF is to replace existing zirconium alloy cladding materials with an alternate material that does not oxidize nearly as quickly as zirconium, and effectively provides greater tolerance in the event of an accident. So basically, the intent here is to oxidation kinetics to provide increased response time, thereby also reducing cooling requirements in the event of an accident, and also to reduce the release of hydrogen gas, which is obviously very explosive. So this figure on the right from Bruce Pine at Oak Ridge and his colleagues gives a bit of an idea of how these different alloys behave with respect to temperature on the horizontal axis and the reaction constants on the vertical axis, where we have zirconium here in the black line up above, and several of these other alternate materials such as Ficral, which is a type of steel, has several orders of magnitude lower oxidation kinetics. So the idea there is to replace zirconium with one of these other alloys to provide greater tolerance. Obviously, it's not quite that straightforward. There are many other factors to consider, but that's out of the scope of today's presentation. As far as the problem statement goes, Ficral is one, class of alloy with many different compositional variants. Has been pretty extensively studied in predominantly the United States and also in Japan. And there's been some commercial exploration of that as well. However, another related alloy, Ficral oxygen dispersion strengthened, ODS, has not been nearly as extensively investigated. So the objective really in this work was to explore the oxidation kinetics of Ficral ODS and how does that oxidation layer form. The experimental work that was involved in this project was twofold. The first was the actual thermal oxidation process, which was accomplished with a Netzsch 449 F1 Jupiter Simultaneous Thermal Analyzer, in this case only done in Thermo-Gravimetric Analysis mode. And we used 2 furnaces that we have installed on this machine. The first is a silicon carbide furnace capable of reaching upwards of 1550 C, but for this case we went up to 1400 C. And the other is a water vapor furnace that's capable of providing high quality steam upwards of 1250 C. The second stage of experimental investigation was in characterization. This was done at the University of Toronto, some of their user facilities, where we used scanning electron microscopy with electron dispersive spectroscopy techniques and electron probe microanalysis, EPMA. As far as the TGA measurements go, like I said, we had a campaign where we oxidized a number of different specimens, both in air and in steam. And there are reasons to do both. One is that the more realistic conditions are done under steam environments. However, a number of previous investigations have demonstrated that the kinetics is, for all practical purposes, equivalent between both air and steam. Nevertheless, we still performed the measurements in both environments to verify this with respect to ODS Ficral, which is slightly different. Admittedly, you can see, the steam measurements are a little bit more noisy than they were in air. This was actually our first campaign where we used the water vapor furnace, and what we believe to be the case is that we were running it at high flow conditions, and steam, having very different thermophysical properties than air, basically results in a significantly higher Reynolds number within the furnace. So we believe that The reason why it's so noisy here is due to turbulence, but somewhat speculative at this point. Nevertheless, the TGA results show that FeCral ODS shows somewhat comparable oxidation kinetic behavior to other FeCral alloys reported in the literature. A little bit worse at lower temperatures, a little bit better at higher temperatures, but roughly in the same ballpark. You can see that we have here the FeCral ODS superimposed here, and both air and steam conditions are shown, which are practically equivalent. Now the photographs on the right show 3 different specimens: the as-received alloy, obviously unoxidized, and then 2 specimens next to it show the 2 different specimens from the same batch, and were subjected to exactly identical thermal ramps, but quite interestingly shows markedly different oxidation behavior. You can see the one on the far right looks more like it's like lava almost. So the results were quite interesting. In the more extreme case of more severe oxidation, we call it the caveman. It looks kind of like a caveman. That's mainly thanks to Ksenia, who did these measurements. And we have 4 different regions that are shown right here in this oxide layer that were examined in a little bit closer detail. So we take a look at alpha, the alpha region here. We can see what was expected. Predominantly an alumina layer that forms in between the base metal and the bulk material there. Not too surprising. However, in the beta region, which appears to be roughly the same looking at the larger scale image on the left, but shows a markedly different oxide layer. In this region here, we can see that there is a, sure you have this like alumina layer, but you have a much more complicated set of iron-rich and some more in alumina-rich oxide layers. Moving on to the gamma region, where we start seeing the presence of some of these inclusions. Again, the inclusions mostly related to the ODS component of the alloy, where we see a lot more yttrium or yttria and zirconia, especially in some of these regions here. So and then I guess I don't have the delta region, but again, you can see that it's rather complicated. And then on top of that, what's worth noting is that in this region, not too surprisingly, it can be incredibly porous, especially in some of these regions. Lastly, we performed thermodynamic modeling to try to interpret the experimental conditions that were done here. This was done using the OECD Nuclear Energy Agency Thermodynamics for Advanced Fuels International Database, or TAFID. And so this was used to try to predict the evolution of different phases under isothermal conditions, but by varying the oxygen potential. So at low oxygen potential, we have predominantly a BCC phase that forms, which is not entirely surprising. And as the oxygen potential increases, we start getting corundum forming. So, predominant alumina, not too surprising there. But then at minus 440 kilojoules per mole, we start getting a liquid phase that forms. So this starts to make sense. And when we see the high porosity regions in some of those oxide layers in the previous figure, but interestingly enough, the calculations predict a combination of both BCC and spinel at higher oxygen potentials, and then again this liquid phase region forming, where again you see a lot of high porosity in the experimentally observed measurements. So again, these are models, but it is an interesting way to interpret what actually happens in the oxidation process. So to conclude, case A, the oxidation behavior of FeCral ODS is generally appears to be similar to FeCral, roughly the same order of magnitude. Again, a bit better at higher temperatures, a bit worse at lower temperatures, but all together roughly the same. But what's rather interesting is that the oxide formation appears to be inconsistent. We verified with our partners at Nippon that all the same specimens came from the same batch and from the same sheet stock, and yet there's markedly different oxidation behavior under identical conditions that are carefully controlled by the Netzsch Proteus software. And lastly, the thermodynamic modeling provides a useful tool to try to interpret what's going on with the results. Case study B is is a different project that we had. Instead of looking at conventional nuclear power reactors, we're looking at a rather unconventional concept of fusion reactors. And at the moment, there are no commercially operating fusion reactors, just some test reactors, some prototypic ones used mainly for research purposes. This work was mainly done by Bernie Fitzpatrick and also Umar Shahid, a former student research assistant, in collaboration with Jim Davis at the University of Toronto and Chris Krobach from General Atomics. So thank you very much to the reviewers. This work is documented in a paper that's currently in review. I forget the exact journal, I think it's American Nuclear Society, Fusion something something. So in this case, this investigation relates to the D3D National Fusion Facility, which is operated by General Atomics in California for the United States Department of Energy. This is a tokamak research facility that's really looked at trying to investigate various properties for fusion energy production. Photograph is shown here on the right. Now, as far as the problem statement goes, during the operation, there are co-deposits and flakes that form after some time of operation from these graphite tiles, which you saw in the previous photograph. And tritium is one of the components on these co-deposits and flakes. Now, what's interesting is that tritium in this context is both an asset and a liability. It's an asset in the context that it's extraordinarily expensive to procure tritium. It's about $40,000 Canadian per gram, or I think some over the order of $1 million per ounce. Tritium doesn't exist naturally and also has some security issues associated with it, which causes or contributes to part of its liability. In addition, there's also safety concerns whereby some of these flakes and dust may form like a potential explosion hazard. So the question here is, can tritium be effectively removed from graphite tiles via thermal oxidation? And whereby, if this is recovered, it could go to, let's say, a recycling facility for further usage. This builds on work from Bernie Fitzpatrick's PhD thesis, where he did some more preliminary work in this regard, what he calls a self-baking oven, but seemed quite promising. So to give a big picture overview of what happened here in this project, there was a Thermo-Gravimetric analysis performed at Ontario Tech using the Netzsch 449 F1 STA, which mentioned in the previous campaign. We used a graphite tile that was donated by General Atomics. This was a used graphite tile that was used in operation, whereby specimens were cut from it and then used for both thermal oxidation and then subsequent characterization. The characterization work involved both X-ray photoelectron spectroscopy at OCAM at the University of Toronto, and also laser thermal desorption spectroscopy at UTIUS, which is the Aerospace Institute of the University of Toronto. As far as the TGA experiments goes, so several specimens were cut, as shown on the previous slide, and would undergo thermogravimetric analysis. On the figure here on the left, we have time versus the mass change in terms of percentages. So you can see relatively very small changes in mass, and this is accomplished by the extremely fine precision of this the mass balance of the F1, which is 25 nanograms. And you can see here there's a vertical dashed line corresponding to the that separates the gaseous environment. On the left, it's pure argon. I believe it's a 99.999% argon. And then on the right, we switched the gas stream to basically air. The three different specimens here are shown, A, B, and C, different temperatures. Now, however, what was clear after this campaign is that it was a bit difficult to differentiate between the removal of hydrogen or H2, which is also known as deuterium, or H3 tritium. So yeah, it's difficult to distinguish between the removal of those elements and also the pickup of oxygen. So we were able to, so this really represents not so much the release of hydrogen, deuterium and tritium, but rather the net change in mass. which also includes oxygen pickup. So to couple this with some other techniques was rather important. The deuterium removal was measured using laser thermal desorption spectroscopy, where the specimen was then placed inside this unit under ultra-high vacuum. A laser was used to ablate a small section of the specimen, and then a quadrupole mass spec would be used to measure the deuterium content before and after oxidation. So this was done for all of the specimens shown here. And so the general trend, which is quite clear, is that thermal oxidation consistently reduces the deuterium content. The degree to which the amount has changed is rather different, but there's a pretty clear trend in that regard. Also, this work was coupled with XPS, as mentioned earlier, and part of the intent there was to examine the surface, to perform surface analysis on these specimens. More specifically, the boron content and boron pertaining phases on the surface. So boron is introduced into the system, not on the tiles, but in the gaseous stream, with the intent of it being an oxygen getter. The figure on the right shows the various binding energies of the specimen, whereby the two vertical lines correspond to two different compounds, the green line being boron carbide and the orange line being boron sesquioxide. The blue squares correspond to a pre-oxidized specimen, and the red circles correspond to a the red circles show the same specimen, but after it's been oxidized. So the main takeaway here is that boron carbide is indeed present prior to oxidation, and then after oxidation, the boron remains, but has been predominantly oxidized. So it seems like it did its job as an oxygen getter, but it's worth noting that we have verified that the specimen did pick up oxygen. So the conclusion of case B with regards to tokamak thermal oxidation, the thermal oxidation process was indeed an effective method to remove deuterium and tritium at modest temperatures, which is rather valuable when you consider that it acts on all surfaces within that system, thereby acting upon gaps and crevices within the system, which can be rather difficult to do with other techniques, and also that there's no need for physical entry, which makes things very practical. The other main takeaway here is that this is, I think this emphasizes a multi-pronged approach to different complementary experimental techniques. And this was evidenced in this project, combining TGA, XPS, and LTDS. I guess like in a future type of project, Netzsch does offer quadrupole mass spec to look at the gas evolution from the STA to look at off gases. That would have been valuable for this one to look at carbon monoxide, carbon dioxide, and different water vapor, which may potentially, likely involve deuterium and tritium compositions. Now, the last case study is regarding the molten salts. So the first case study I looked at was an advanced nuclear material, but for existing nuclear power reactors. The second case study was for a certain type of reactor, a fusion reactor that is, has a much lower technology readiness level. And this one is, I guess somewhere in between with regards to these molten salts. So at the moment, there's a lot of interest worldwide for these advanced reactors, particularly in the form of these small modular reactors. Here in Canada, we have Terrestrial Energy as one SMR vendor that is basing their design off this MSR concept. And there's been a lot of traction on that in the last little while. And the work that I'll be showing here is mainly from Ksenia Lepkina's master's thesis at Ontario Tech. So thank you, Ksenia, for all your hard work. So at a high level, this molten salt reactor is one of these Generation 4 concepts that's being explored. The Generation 4 International Forum is looking at 6 different concepts for next generation facilities. And this one is markedly different than other types of reactors in that both the fuel and the coolant are liquid. In pretty much every other design, the fuel is solid, and that the coolant is either a liquid or a gas. This is the only one where you have a liquid fuel. And so it poses a number of opportunities, but also a number of challenges, because that means that there is no longer a physical barrier between the fuel and the coolant. They're one. As I mentioned, here in Canada, we have Terrestrial Energy as one of these vendors that is exploring an MSR, small modular reactor concept, and they've been selected recently by OPG for further evaluation in their electric utility program to deploy SMRs in Canada. Also, the government of Canada recently announced a major $20 million, investment for their development. So there's been a lot of activity in Canada. As far as the problem statement goes, chemistry and corrosion is perhaps more of a area of study than it is for other types of nuclear concepts. And again, the main reason is because you no longer have a physical barrier between the fuel and coolant. So the main question there is that now that means that not just the fuel, but all the fission products that form throughout the course of a radiation are now exposed to the entire core and all the salt-facing materials. So that enhances some of the chemistry and corrosion concerns. And the figure here on the right is a knowledge gap assessment of the thermodynamics of various fluoride salts. It's not quite a full assessment, but it's it makes the point extremely clear that there's not nearly as much known in regards to the salts compared to there's a big difference between what is unknown and what is known in regards to these salts. Doesn't mean that that's any type of showstopper or any of that, but it just means that there's a lot of knowledge gaps to be filled here, and our intent is really to start filling that up, especially with some colleagues both in Europe and the United States. As far as the experimental overview goes, we've been relying very much on the same STA that was mentioned in the previous two case studies. This one here, we've used exclusively the silicon carbide furnace. And you can see here on the left is a photograph of our unit. Notice that there's the two furnaces there, so we can switch them pretty easily. We also put on a Xerox oxygen probe, so we can measure the oxygen potential downstream, which is an incredibly useful feature, by the way. And another component we've been relying on heavily is an oxygen trap system, OTS. That's also a Netzsch product with the intent of you put that basically on your sample carrier to get our oxygen. It works very effectively at higher temperatures. Now, one thing we've noticed is that this is particularly important when you get to higher temperatures and if you're using any type of steels in this environment. On the top here, we see the two crucibles that we're using for these fluoride salts. What we've done is we've used a retrofitted crucible from Netzsch in this regard. Notice that there are two because we're using a DSC mode. When you're using a DSC mode, you need to have one for your specimen and then an identical crucible that's empty as a reference. So the big problem that we had in this work was getting a crucible that works and is compatible with fluorides. Fluorides are incredibly chemically reactive and quite hygroscopic. So there's a few concerns there. One of which is that if you have, let's say, an open crucible in air, the specimen itself could oxidize rather easily, even under low oxygen partial pressures. And then there are two additional concerns, one of which is any type of off-gassing. First concern is interaction with the STA furnace or any other components. And then the last concern is obviously the health and safety of the operator and other persons in the room. So you may notice from the previous slide, we have a elephant trunk that is directly above the STA. Depending on the experiments, we also have a gas line where we plumb it up directly to the STA into our exhaust system. But anyway, so the main concern is that we need to have a crucible that is compatible with fluorides and preferably, get up to pretty high temperatures. So unfortunately, there wasn't, even though the Netzsch catalog for crucibles is extremely comprehensive and has a plethora of options for various applications, none of them were directly applicable for fluorides and that are compatible with fluorides, that can maintain a hermetic seal and can get up to at least 1,000 degrees C. So what we've done is we actually retrofitted a commercially available Netzsch crucible that's shown here on the left. where we have the body of the high pressure stainless steel crucible with the corresponding crucible lid. Now note that this product is actually recommended by Netzsch to be limited to 500 degrees C. It comes with some gold gaskets, and the intent is for it to be used up to 5 times, whereby after each use you just punch out the gold gasket with this little hole here, and then you're good to go. So what we've done, to be very clear, is we have gone against those recommendations, and so this is I guess treading on our own territory here with our own risks and all. But what we did is we retrofitted it by creating these custom liners made out of nickel 201 and a nickel gasket also made out of 201. So this liner, you can just pop right into this crucible, and then you put this gasket here. We have this this liner shown right on here, and then we've been making our own gaskets with a punch. This is actually made, I think, for jewelry or something like that. This idea, I believe, was from Caitlin Collin from University of South Carolina. So thank you, Caitlin, for the idea there. So anyways, you can punch this. We use that with our a hydraulic press in our lab, so it's been pretty repeatable. We have, in another conversation, I can go into additional details where we've demonstrated that it maintains a hermetic seal under operating conditions, and we've experienced that this works well up to 1200 degrees C, which is excellent. The only caveats are that you have to be very careful with the oxygen environment, so you want to make sure you eliminate any oxygen from the atmosphere, bring the oxygen partial pressure down to like 20 or 30 parts per million. It has been proven effective, and then periodically you got to clean up the sample carrier. Okay, so sample preparation. These fluoride salts are pretty hygroscopic. So what we've been doing is performing all operations within our glove box. And for anyone that's used one of these glove boxes, it kind of breathes in and out a bit. So we call this an Anakin, just like Darth Vader. You can see a little Darth Vader bobblehead up on the top there. So all operations are done within the glove box, which typically maintains an oxygen and water vapor partial pressure of about 0.5 parts per million. Pretty dry in there. Even these as received fluoride salts, we find that even that the vendor claims super high purity, they're so hygroscopic. Even just in transport, we find it's necessary to further purify them, which is a pretty straightforward process, and just heating these guys up within the glove box. So that's accomplished with putting the specimen components within this nickel 201 reaction vessel, and then put it in a sand bath on top of a hot plate, and you heat it up within here, and that usually does a pretty good job. Dealing with the actinoid fluorides is much more problematic, which we're currently investigating. So then after this is all purified, then it's decanted in one of these crucibles with the nickel liner. For multi-component salts, we'll use a mass balance to achieve certain compositional ranges. This right here, you see the crucible sitting inside of a Netzsch crucible press, which is needed in order to not just close the crucible and take it off, but what's important is that it has a torque wrench, so you can ensure that you tighten it to a consistent level of torque. So that's been found also to be rather important for reliability purposes and ensuring a hermetic seal. Some results are shown on this slide. This is mainly the outcome of Ksenia's master's thesis. We went through since we're using a crucible far outside the intended purpose, the first thing to do was to benchmark. So we went through a benchmark campaign with respect to known values. The figure on the right shows FliNak, basically a ternary mixture of lithium fluoride, sodium fluoride, and potassium fluoride. This was kindly donated by the Oak Ridge National Laboratory, and the melting temperature was determined to be, within a fraction of a degree of reported value. So that was great. We did the same with other pure component salts, and also some mixtures here. So on the left, you can see some work with lithium fluoride, cesium fluoride, cesium being an important fission product in the context of nuclear reactor safety. And again, this was mainly done by Ksenia in her master's thesis and additional experimental measurements, which she's writing up the paper now, and hope to send it to a journal soon. Now, the other caveat with this, with respect to this crucible, is that like it works great for melting point determination, but not so much for heat capacity. And so this wasn't really surprising, mainly because the integral heat capacity of the crucible itself is relatively huge with respect to the specimen. So we expect that thermal lag will be a major factor here. The crucible with the lid, the liner, and all that, I think it was something like 1.1 grams or so, but it was definitely over a gram. So, I mean, that was relatively heavy. So if you consider in comparison, a graphite crucible from Netzsch with the lid is about 0.09 grams. So that's more than 10 times the weight of a graphite crucible. So not too surprising. So we don't quite have a solution yet for heat capacity measurements of these fluoride salts, at least in regards to trying to get these high temperatures. So in conclusion, for the fluoride salt chemistry work, we were able to design a new crucible and tested it under a number of conditions. Retrofitted a commercially available product with some custom components that were relatively simple, straightforward, reliable, and works with fluorides. And we've had experience with upwards of 1200 degrees C. So it's, I say that it's not, in that regard, it works pretty well, but you also have to be very careful, again, of your gaseous environment. And you also have to clean up your sample carrier every now and then, but it does work, which is great. We have tried several other prototypes before that didn't work out quite as well. So I was glad to see that this worked out. Heat capacity didn't work out quite as well, not surprising. So work is ongoing and trying to design a new custom crucible that really has three objectives. One is to further reduce costs, two, to be able to reliably measure heat capacity, and three, preferably reach temperatures upwards of 1600 degrees C. So general conclusions of the talk. So the Nuclear Fuels and Materials Group at Ontario Tech is conducting a number of research in advanced nuclear fuel or materials with a focus on fuel performance and safety. You can see these three different case studies all relied on using this Netzsch Simultaneous Thermal Analyzer. It's been a great workhorse. We've got a large number of activities. I mean, we've used this so much, like sometimes it's running right through the weekend and right in the evenings. And I got to say, like, Netzsch customer service has been first rate, so thank you very much. And last thing I wanted to mention was if there's any folks in the industry looking to hire talented and team-oriented students, please contact me. Ksenia, who just I mentioned a number of times here, she did a lot of the work in today's presentation. She just graduated and is looking for a job. So if you're interested, please contact me and I'll put you in touch with her to be a great addition to your team. And same goes for other students as well. So thank you very much. Appreciate your time. If you're interested, feel free to check out our group website, and or if you want, feel free to send me an email. Both are provided here on the screen.
Thank you, Professor Pirro, for your discussion on the thermal analysis of advanced nuclear materials. You're still able to ask questions. We have one question.
I like Umer's question.
Yeah. Yes. So whatever happened to zirconium hydride to reduce hazards?
Okay. The only thing zirconium hydride to reduce hazards. What I think that is intended there, or maybe the question was referring to, is that there's a number of work in looking at coated zirconium alloys. There are a few different variants of these different types of coatings, like chromium coated. Perhaps this is what the person was referring to, where the French in particular have been looking at coating their existing conventional alloy with chromia, which provides greater tolerance in the event of oxidation.
Good. Also, how is the boron introduced as a getter?
That I don't know. I'd have to defer to my colleague, Bernie Fitzpatrick.
Okay. And how many uses do you get from the nickel liner that you created or that you made yourself?
So well, first of all, the liners we had outsourced to a local machine shop, and we found that it very much depends on the use temperature. One of the problems with the design is that especially once you get up to like above 1,000 degrees C, the steel lid almost welds to the steel base, which means that it's effectively single use. The other thing is that, and we can make a slight change in the design with respect to the gasket. The gasket probably could be made a little bit smaller in diameter. It's really hard to get the gasket out. So for a number of applications, it's single use. Having said that, I think with some minor design changes, it could be made to be multiple use. We have not yet made a thorough campaign to quantify the differences in the specimens when using it for multiple times.
Okay.
So long story short is I'm guessing less than the 5 times it's intended to be used, upwards of 500 C.
Good. And back to the original question, when it said, whatever happened to the zirconium hydride to reduce hazards, the follow-up to that question from the same person says this was used as a co-ingredient in fuels. I don't know if that changes anything you want to add.
Not a whole lot. I mean, I'm aware of some like uranium hydride, uranium zirconium, some mixtures in that regard, but I don't remember anything really going past that. But I mean, that may be just my own, either I'm not remembering it, or at least it hasn't been investigated very heavily.
Okay. And our final question is, have applications for silicon carbide and molten salt applications been identified?
Not that I'm aware of.
Okay, good.
Silicon carbide has been used quite a bit in some of these other advanced nuclear materials that have been proposed, in particular as a candidate for accident tolerant fuel cladding. That's been mainly explored by like Westinghouse, and also as a material in trizo fuels.
Okay, good. That's all the questions we have. I want to thank Professor Pirro for his discussion and presentation today on the thermal analysis of the advanced nuclear materials. I would also like to offer our appreciation to everybody for joining us today for our Research Spotlight series. If you have additional questions on this presentation or anything in general concerning these Spotlight presentations, you can email us at nib-spotlight@netzsch.com. We'll be starting our next series of research spotlights in December. Any of the previously recorded presentations are available for the one on polymers and the one on metals. So please join us again in December for these informative presentations on how you, the customer, use thermal analysis. Have a great rest of your day, and goodbye from Netzsch.